Hi everybody, welcome to this course on applied statistics. This is the first lecture, and in this lecture we shall introduce why do we need to learn the subject matter of applied statistics, the breadth of topics to be covered, and the types of information that we can capture in statistics. So let's start by asking why we need to learn statistics. So I shall summarize my response by stating that statistics is the scientific response to uncertainty. And everything I say from here onwards will exemplify that. For example, suppose during a widespread pandemic, the educational institutes need to decide whether to teach face-to-face or online. So they question, do students like to study face-to-face during a pandemic? The answer to that is unknown and hence represents uncertainty. So how do we resolve this uncertainty? Well, one approach is to simply hazard a guess based on our individual understanding. However, a statistical response to this question will be to survey the students in such a manner that the answer reliably estimates the response of the overall student body. A reliable estimate is important, and how to produce that reliable estimate is the domain of sound statistics. Statistics is also a way of scientifically testing beliefs and theories. Suppose we want to test if breastfed babies grow up to become more intelligent than the formula-fed babies. Now, how can we reliably test that? How do we collect the data and test our hypothesis? And what magnitude of difference in intelligence scores will be enough to decide the argument? Is a 1% difference enough? Or should it be at least 2% or even more? Or is even a less than 1% difference sufficient? Also, a very important question is, how many people should we observe? Statistics provides the answers to those questions and provides us with mechanisms to reliably and hence scientifically decide a data-oriented debate. Reliability that sound statistical measures bring can also produce ethically better decisions. For instance, to resolve the statistical questions that we posed in the previous slides, how should we collect our data? Should we collect it all from our friends and family? Should it be only from a certain city, region, country, or continent? Should it be only from a particular ethnicity? Statistics relates all those aspects with the broader statistical question that we are trying to answer and enforces that whatever data that we collect must represent the entire population about which we want to draw a conclusion or make a statistical hypothesis. Clearly, statistics enforces representative diversity into the dataset, and that is ethical. Statistical methods are often used to identify key drivers behind an outcome. Often the same methods can also predict the outcome where the outcome is unknown. For example, consider the university guide produced by the Guardian newspaper, and it ranks different universities based on a Guardian score. This score is calculated by considering many factors or variables that are visible on this slide. Now, question is, which of these variables influences the outcome score more than the others? That's a question that statistical methods can answer, and we shall discuss some of those methods later in the course. So essentially, statistics guides us on how to collect data, analyze data, and report results using proper methods. It also helps us make scientific discoveries, data-based decisions, and predictions. Moving on, in this course, we shall cover the topics as given on this slide. In these bullet points, I first give a common description of the topic and then put its formal name in italics. So we shall look at aggregating information, that is measures of central tendency, spread of information, that is various data distributions, how to collect information, that is surveying and sampling, testing beliefs, that is hypothesis testing, associating different pieces of information, that is correlations, and predicting outcomes, that is a process called regression. However, since all statistical methods rely on data, let us conclude this lecture by discussing the different kinds of data in statistics. The first kind of data variables are those whose values represent some class or category. So binary variables are those whose values always fall in one of two categories. For example, alive or dead, on or off, absent or present. The next type is called nominal variables. Sometimes they are also called just categorical variables, although all the variables in this slide represent categories. Their values simply represent categories, but there is no logical order between these categories. Hence, no value is better or worse than another value. For example, ethnicity can be Asian, African, white, or some other value. Likewise, dietary styles can be omnivore, vegetarian, or some other value. These are all just categories, but we cannot assume an order among those values. Note, binary variables are also nominal variables. They just represent a special kind of nominal variables. Values of ordinal variables also represent categories, but there is a logical order between those values. So you may be unhappy, happy, or very happy with this lecture. And clearly we can see a logical order of preferences in those values. However, we cannot calculate a numerical interval between these categories meaningfully. For example, what is the interval between unhappy and happy? And whether that interval is the same as that being happy, as that between happy and very happy. We cannot really say. The other kind of variables are continuous variables. These variables have values that are typically distinct because they come from a large or even infinite range. For example, temperature, weight, and height are continuous variables. Among continuous variables, there are again two kinds. Interval variables are those where the intervals between values make sense. For example, temperature interval between 8 and 6 is the same as that between 15 and 13. Unlike ordinal variables, here we can compute the differences meaningfully. However, when the value of an interval variable is 0, it does not signify the absence of this variable. For example, 0 degrees Celsius does not imply absence of heat because clearly objects can get even colder. So 0 for interval variables is just another value. Because 0 does not signify the absence of variable, the ratios of values is also invalid. For example, 100 degrees Celsius is not twice as hot as 50 degrees Celsius because heat begins at minus 273.15 degrees Celsius, and therefore the heat interval of up to 100 degrees Celsius is not double that of up to 50 degrees Celsius. In contrast, ratio variables are those interval variables where a 0 value means absence of the variable. For example, 0 height means no height. Therefore, 12 feet is twice as high as 6 feet. That is to say that the ratio of 2 or twice makes perfect sense. I'll wrap up this video by asking you a couple of questions. Is temperature measured on Kelvin scale a ratio or an interval variable? To decide, think if 0 Kelvin means complete absence of heat. You can pause the video here and reflect. So I'll resume. The answer to the question is yes, as per the laws of thermodynamics. And hence Kelvin scale indeed represents a ratio variable. Likewise, how about a variable that measures the difference between two identically measured quantities? Again, a value of 0 means absence of difference. Therefore, difference is a ratio variable. So with that, we conclude this lesson, and we hope to see you in the next lesson. Thank you.